Here's a walkthrough video for Lab 9. Okay, in Lab 9, we're coming up with a circuit that's called an Arithmetic Logic Unit. Okay, so that shows up here. And the idea here is that we can give various codes through a switch input to make our system do whatever operation that we've programmed it to do. So in our case, we've looked at operating on operands N1 and N0. That's the input to the ALU, N1 and N0. And the operations that we can do are add, subtract, and, or, and exclusive or. Okay, so mathematically I ran through a couple of example inputs. If you put N1 to be 6F and N0 to be 3A, these are the resulting operation outputs that you should get. Okay, so let's think about how this whole system should work. Now, we talked about this in class, that we only have a limited number of switches on the basis 3 boards. So we are going to use a register to put the operands into the ALU. So let's talk about how that would work. So let's say I wanted to put into N1 6F, the first operand. Okay, so I would configure the switches so that I have a binary equivalent of the hex representation 6F. Okay, now that would be applied to the register, and when I press the button down on the basis board, button D, okay, that should clock, by pressing the button, you're enabling that to store in this register 6F. Okay, so you're moving that data into 6F. All right, and then of course 6F goes to the output here. All right, so that's the output of Q, which is the input to the ALU. All right, so that's how we get our first data point. Okay, and nothing's been sent to the output yet because I have to, press the button up, this button, in order to clock the output from the ALU into the output register. Okay, so nothing's happened yet, or it shouldn't have happened yet, as far as the output is concerned. Okay, so once we press that button, it's no longer asserted, but 6F is stored in the leftmost register. Okay, from there, you can put the next input. Okay, so in this case, I've worked out, I can use the switches to configure 3A to be the next input. Okay, so now we're ready to go. Now we're ready to have an operation. So if I wanted to do an addition, I would put all zeros here on these 4 switches because that selects the AND operator. Okay, I'm sorry, add operator. All right, so from there, I've got it all set up. What I would do is I'd press the BTNU button, okay? And so 3A is already applied to the input of the ALU. The ALU is combinational, okay? All right, so then I would get the operation performed. I would get, if I have all zeros on switches 11 through 8, I would get an addition, and A9 would show here. And since we're asserting this button, the enable line is asserted, and the resulting output of the addition, which I calculated in advance to be, well, we know that is A9. A9 would be distributed to the LEDs, and you'd see, the right buttons lighting up on the board where you'd see the no light, light, no light. Okay, so there's the A, and then all right, so maybe a better way to draw that would be with circles with no, not colored in. right, so this would represent the 9, and this would represent, the A. Okay, so hopefully that shows how this circuit is operating. In the meantime, there's always a system clock that clocks things in, but we're controlling the operation with this with these U, D, and C buttons. All right, this button clearly, it just clears everything. It clears the register, so we're ready to do our next operation. All right, so that's kind of the top level overview of what's supposed to happen. And what you'll need to do is you'll need to build modules for both the top level that we're showing here and also for the lower levels. All right, so that would be an instantiation of the storage registers here and here and the ALU. Okay, so let's talk through that a little bit. All right. So we'd mentioned this in class. We'd gone over HDL code for making a D flip-flop, and a register is just a sequence of D flip-flops. All right, so the things that are noteworthy here are, once again, we're doing a parameterized module. All right, it has a default value of 1, but here we go, we can change that. And in fact, we ask you to change that to a couple of different values within the lab. All right. There's going to be a system clock, there's going to be a reset, and there's going to be an enable line that is controlled by the buttons. All right. The system clock is coordinating the transfer of things within our system, and we talked about that in class, that synchronous systems need a clock. All right, so we define inputs, D, and outputs need to be a register, and we'll call that Q. All right, so the key to filling out your part is to look into the notes. We've actually, in one of the lectures, we covered a D flip-flop with an asynchronous reset. All right, so that's what we're talking about here. That says this in the notes. So because it's asynchronous, the reset needs to be active when you get a positive edge on reset. So that's why that's in the sensitivity list. The clock is also in the sensitivity list. All right, but for the enable, we only want things to happen whenever enable is inserted. Enable is not in the sensitivity list because we are wanting things to be clocked on the enable input. All right, reset is asynchronous, enable is synchronous. All right, so there's nothing hard about this. I don't want you to fret over this statement, but if you go look in your notes, this is fairly obvious what needs to go here. It's just the operation of a D flip-flop in a register configuration, a sequence of D flip-flops. All right, so there's that. The next thing I wanted to talk about is the unique things that are coming up that we haven't seen before in terms of a test bench. All right, the unique thing is we need to come up with a clock. All right, so this couple of lines of code gives us a system clock that we can use to test our circuit. Okay. Next, the next thing we need to do is to actually test the register that we've instantiated. Okay, and so in this particular test code, we are doing a parameterized instantiation of the register. So it looks like we're doing 4 bits here. We have some initial things that run just that one time. And so we initialize the clock, but then this particular set of instructions will get that clock generating always. It's in the always block. Okay? And so we have some initial conditions that we have starting here with enable equals 0, reset equals 0, and the D flip-flops in the register initialized to hex 0. All right, so then we're testing. Put a reset equal to 1, data into the register with this line. And so you can go through there and you can look at the timing of this and sort of, you know what a D flip-flop is supposed to do. All right, and so from there, you should be able to fill out this table 9.1 expected results table. Okay, so it's marked up in terms of clock periods. All right, if you go back here and look, the clock was set with a 5 parameter. Okay, so we're seeing multiples of 5 showing up across the rows of the timing for the expected results table. All right, so your task is to fill in what goes here based on what you know about D registers. All right, and then when you run your test bench, make sure that matches. All right, remember the whole point of the expected results table is to know, conceptually what the result should be, and then verify that with the simulations. Okay, so the next thing I want to talk about is the ALU module. Okay, so for the ALU module, we need to have the different operations programmed in, and we're again doing that with some parameters that make it easy to change if we wanted to, for example, add different types of instructions, or resequence how we want to decode those with the switches. All right, and so in this case, this is essentially combinational logic, right? And so we've done this before with procedural type code. So we have everything in the sensitivity list, okay, that's with the star operator. And then we just add various cases based on the operation parameter, okay? All right, so an operation parameter is a 4-bit input. All right, so one thing that is noteworthy also is that the plus sign, we went through a whole sequence of labs where we looked at adders. And so a natural question would be, don't I need to do that? Don't I need to put in all my old code for an adder? And the answer to that is actually no. This will actually get implemented from the HDL. All right, so remember, our old labs were really getting you up to speed on how all this works. And so we were doing things at a level that you wouldn't typically do. All right, typically, if you want an adder, you would just give an add operation and you'd count on Verilog and the tool to correctly synthesize an appropriate adder. All right, so how that synthesis works, that's really kind of deep under the hood. We don't need to worry about that yet. And so that's good news for this lab. These operations are pretty simple to fill in the codes that you would need to implement those operators. Okay. All right, so hopefully that's helpful to you. All right, and let's see if I wanted to cover anything else. Those are the main things I wanted to touch on. We'll talk about this more in the lab, and good luck with getting this working. We have a couple of weeks here, and there's not a lot of coding, so I'm hoping everybody can kind of get caught up and back on track for completing Lab 9 so that we can finish Labs 10 and 11 in a timely way.